Radar-absorbing materials are a relatively old concept. They are actually as old as the radar itself. The first experiments go back to the 30s, and the first practical applications happened during the Second World War. Some German submarines had the periscope coated with radar-absorbing material, evading the Allied airborne radars. The research and development of these materials has progressed for the whole Cold War. And indeed, the progress has been spectacular, obtaining materials that can cause an attenuation of the radar reflection up to 50 or 60 dBs. Actually, these incredibly effective radar-absorbing materials can be purchased by anyone on the normal civilian market. Yes, because we are talking about this type of materials, which are used in anechoic chambers to test, well, any kind of radiation-emitting device. Obviously, this is not what we are interested into, but I want to stress that there is no real secret about the mechanism that can be implemented to create the radar-absorbing material. The secret is how to create a material that can be used effectively on a combat plane and the details of its tuning. I'm the Crow, welcome to Millennium 7 Star, the channel that helps you make sense of military history and military technology. The propagation of electromagnetic waves is conceptually a complex subject, which is beyond the scope of this video. What we are interested are the conditions in which we have a reflection. So this happens when there is a discontinuity in the impedance of the medium. The impedance is the measure of how much a medium opposes the propagation of a wave. It is often used to characterize electronic components like resistors, capacitors, and inductors, but even the empty space has an intrinsic impedance. When an electromagnetic, that is a radar, wave hits a surface, if the material has a drastically different characteristic impedance from the almost empty space in which it was propagating, like it happens for example with a metal or a semiconductor, then we have reflections. There are actually three conditions under which the reflection can be zero. The first is when there is no discontinuity of electric properties in the propagation, a condition which is also known as impedance matching. For the empty space, the intrinsic impedance is about 377 ohms. It is not difficult to obtain a material like this, plastics for example, but also wooden frames with fabric like in World War II. Problem is that often they can't be used for a reason or another in modern aeronautic construction. And if they could, the wave would go straight through, and if it finds metal underneath, well, it is reflected by the metal. Considering that with the current technology level, at least the engine must be made of metal, well, this is a non-starter. The second condition happens when electric permittivity and magnetic permeability are equal in the material. These are constants that characterize the material behavior with electric and magnetic fields. This equality could be something very difficult to obtain from just a piece of material, but there may be some active techniques, that we'll discuss later, which could use these mechanisms to minimize the reflection. The third condition is verified when the material is thick enough to dissipate the radar wave. If a wave goes straight through a material, it doesn't mean that nothing happens. The wave still interacts with the material, and its energy is slowly dissipated. The dissipation is measured by an attenuation coefficient. The coefficient is high when permittivity and permeability are high, but this will end up breaking one of the two previous conditions. If the attenuation coefficient is low, then the material is probably going to be too thick for a practical application. So in practice, there is no material that we can really use to satisfy these conditions. We must create some sort of contraption to make one of them become true. These contraptions are called metamaterials. The simplest metamaterials are the absorbing materials. That is, those that try to have a high dissipation. They go under the popular name of iron ball paints. The principle is to have a non-conductive matrix, like a polymer, filled with small spherules made of iron, steel, carbon, or any other conducting materials. The molecules in the spherules resonate with impinging radiation, they start vibrating, and dissipate the energy, warming up the matrix a little bit. This kind of materials has been used on the F-117, and we know this for sure, in the form of a paint and a glue. Material like this can obtain on its own an attenuation of about 10 to 15 dBs. Obviously the exact numbers are still a secret, but 10 dBs is nothing to write home about. There has been also a lot of research on these paints. There are versions with flecks of metals, others with an assortment of different sized balls. Some may have carbon rather than metal, some may have coatings, but a lot of research has been also aimed at making these paints durable in an operational environment, which is the actual Achilles heel of these metamaterials. Well, the paint is obviously quite practical, but its effectiveness depends heavily from the frequency and the size of the balls determines the frequency where the peak absorption is. In general, American metamaterials for aeronautic use focus on the X-band, which is used by most radars. Other countries are even more secretive about their materials, and we don't really know the choices that they have made. Paints and glues are the radar-absorbing metamaterial most used in aeronautics, but there are more modern solutions which try matching the impedance of the metamaterial. While the paints, from the point of view of the impedance, behave like a resistor, to match the impedance we need a metamaterial that could behave like a resistor, a capacitor, and an inductor at the same time. It is as if a small electronic circuit or a small antenna is embedded in the material. It interacts with impinging radiation, developing currents that are dissipated, subtracting energy to the wave. The material as a whole behaves as if the impedance is matched and no reflection happens. At least this is the theory, because as usual the impedance depends from the frequency, so the material needs to be tuned to a specific set of frequencies. There are a few geometries that have proven to work. The one we know more about is the split ring resonator. The material is made by a lattice of non-conductive material. On the internal surfaces, small rings or squares of copper or another non-magnetic material are printed in a very thin layer with a slit on it. There are maybe concentric rings or small squares side by side, usually arranged in a thickness of 2 or 3 layers. Tuning each layer for a specific frequency is possible to achieve quite a high radar absorption on a wide band of frequencies. These materials have been a development of the last 2 decades, so we don't know exactly where they are used. However, they could be positioned inside the aircraft structure, where there are other areas of composite materials that let the radar waves go through. As far as we know, the American stealth planes have used so far mostly different types of paints and glues. The durability of and the resistance to wear of these materials has been the main issue. The B-2, for example, if deployed overseas, requires a climatized hangar to avoid coating degradation. The F-22 has had a lot of problems with the coating peeling off in particular conditions. The F-35 seems to have improved this aspect, but still a few problems have been reported. 80 or 90% of the stealth effectiveness is to be attributed to the shape, so these materials are actually a complement to the stealth design. Their main usefulness is that they can fill the small nooks and crannies of the surface, like rivet heads, panel junctures, whatever, which otherwise would reflect or diffract the radiation at full force. Well, obviously the research is not stopping, and there are very exotic solutions being studied, like paints based on carbon nanotubes or powdered silicon carbide and so on. For the moment being, though, we stop here. Thank you for watching, and goodbye.